Alright, this is the second section of, or well, I guess the second part of section 1 of chapter 2, which is talking about speed. So that's what we're going to get into. So, speed. Speed, basically, I always think of speed as like, you're driving down the road and it's just how fast you're basically going. So if I hit the gas pedal, it makes me go faster, and so, I'm going really, really fast, and, I'm speeding. And that's the general idea, how fast you're generally going. But of course, in physics, we need to have a more definite definition to, what speed is. And so speed, we have here that speed is going to be the distance that we travel. So we've already talked about what the definition of distance is. So it's the distance an object travels per unit of time. So how far we're going in a certain amount of time. So if you kind of think about that, it's logical, because when you're traveling down a road and you look at something, you go, okay, well, I'm traveling 50 miles per hour. Well, that's 50 miles. Miles is a distance over, 1 hour. Hour is a time. So that's 50 miles per hour. That's a speed. So, speed is an equation. So I have speed, which of course here in physics class we're not going to use miles per hour. So we're going to use actually meters per second, because meters in time, meters is our distance and seconds is our time. And then we have distance over time. So the abbreviated version of what we just talked about is S equals D over T. That's our equation. So of course, since we're using the metric system, sometimes it's more convenient to use like kilometers per hour. That's why if you go to a lot of foreign countries, like for example, maybe some of you've taken a car and driven to Canada, you've seen that a lot of their stop signs, or not stop signs, but their speed limit signs, they're in kilometers per hour. And that's why, because they use the metric system. And that's why your cars, a lot of the speedometers, they have their your units in kilometers per hour as well as miles per hour, because you want to be able to take your cars to other countries. Alright, so let's practice this equation that we just learned. So we just learned that S equals D over T. Alright, so S, D, T are our letters here. Alright, so speed, distance, time. So speed, we're looking for things in like meters per second. Distance, we're looking for things in meters. Time, we're looking for things in seconds. So those are the units we're looking for. If Steve throws a football 50 meters in 3 seconds, what is the average speed, velocity of the football? Alright, so we have 50 meters right here. So meters is a distance. So right now we have 50 meters for our distance. And then the other thing they gave us was 3 seconds for our seconds. Again, seconds is our time. So they gave us 3 for this. So look, we're playing kind of a matching game. So look, the only thing we don't have is this right here, because they didn't give us this unit. So that means that we're solving for S in our equation. So that means when we go to plug in here, we don't have this, we don't have S, but we have 50 over 3. So this is going to be a division problem. So that means you just have to take your handy dandy calculator and take 50 divided by 3, which of course in physics it never works out perfect. So you're just going to give me like one place after the decimal works out. So like 16, it works out to like 16.66666666. So just round it to like 16.7. And so that's in meters per second. Because again, you're solving for S. S has this label, and there you go. let's try another one. Alright, so again, we're going to use the same equation because this is a speed problem. So it's S equals D over T. So you'll have S, you'll have D, or you'll have T. And remember the units that you're looking for these things. So Bart ran 5,000 meters from the cops at an average speed velocity of 6 meters per second before he got caught. How long did he run? Okay, so 5,000 meters. So meters, again, meters is a distance, so you know right here you have 5,000. 6 meters per second. So notice what I'm doing when I'm going through these problems. I'm searching for the numbers. You guys in this class are going to do a lot of that, just kind of searching for the numbers. So 6 meters per second. Meters per second, this is written a little different, but this is the same thing as this. So this time they gave you the speed, so they gave you this. So that means that the only thing you don't have on this one is the t. So that means that this problem is going to be set up where you have 6 here, you have your 5,000 here, and you do not have t. So if you do not have t, mathematically what you do is you just take and you switch the places of 6 and t. Okay, so you actually, the problem, the way the equation is actually set up, it's t is the same thing as 5,000 divided by 6. If you guys want, come hang out with me for a minute and mathematically I'll show you how that actually works if you want. Or just remember that the equation can also be, if you want, t is equal to d over s. Okay? However you want to do it. So that means you're going to take your 5,000 with your calculator, divide it by 6. And so again, we don't get a perfect number. You get 833.3333. So again, just give me a place after the decimal for this class, not a big deal. And so it's a t, so that means it's going to be seconds. So this guy Bart ran from the cops for 833 seconds. And so just for funsies, I'm taking my calculator over here. He ran for about 13.8 minutes from the cops. So that was a little bit of time. He had a good little run. Alright, so let's do one more. So we're going to talk about Sarah here. Again, one more using the same equation. So we have S, we have D, we have T. Alright, Sarah here backstrokes an average speed of 8 meters per second. How far can she swim in 100 seconds? So, again, we have 8 meters per second. So, 8 meters per second, that is a speed. We have 100 seconds. So, that's your time. So, this one you're solving for distance. So, this third example allows for us to solve for the one variable that we haven't solved for. Now that I've given you an example where we've solved for every single variable. We were going to solve for S, the last one we solved for T, and now we're finally solving for D. So, this one we set up, they gave you 8 for S, we don't have D, and we want to solve for, we have T is 100. So now, mathematically, how do you solve this one? When you have S and T, all you do is you take these two numbers, in this case 8 and 100, and you just multiply them. So if you want to think about it, if mathematically, if you want to find D, it's just S times T. Okay. So D is equal to 800 in this case. And D is always going to be in meters. So, there's an example of each one of those. Alright, so let's talk about a couple other things here. Let's talk about some definition type stuff. If you're traveling at a constant speed, that means that your speed is never going to change. So that means you could calculate your speed at any distance interval. Meaning that if I'm traveling along, that means that at this point I'm traveling a certain speed, maybe like 50 meters per second. Oops. I don't know how I did that one. Sorry about that. Get my pen back here. 50 meters per second. If I'm traveling at this one, I'm going 50 meters per second. And if I'm traveling at this one, I'm going 50 meters per second. It doesn't matter. No matter what point I'm traveling at, if I'm going at a constant speed, notice, constant means I'm always traveling at the same speed. At every single interval, I'm going the same speed. Now, normally in real life, that's not what happens. Usually we have a changing speed. And that's what they're showing here with this graph. And they want you to think about it. They're saying, like, let's imagine that you're going for a bicycle ride. And maybe you're traveling like 5 kilometers. Like, for example, maybe you're going to take, a nice little bike ride from, I don't know, here to, Pittsburgh. Well, if you do that, you're not going to be able to just go a constant speed the whole way. You're going to have different parts where you're going to have to slow down or speed up. Or even if you're traveling just maybe even through Lisbon itself, you're going to have to slow down or speed up because of traffic, because of stop signs, because of other cars. And so your speed is always going to be changing. And so that's what they're wanting to show you with this graph here. If you just kind of even look at it, that notice like your speed, here you're gaining speed. You might be going up a hill even. There might be points where there might be nothing affecting you other than the terrain itself. So you're going up a hill, you're going down a hill, so your speed's got to go up. You're stopping for a red light, so then your speed's got to go down. You're going at a constant speed. So all these different speeds are changing. So how would you express your speed in that way? When your speed's not changing, like when the last slide, it's easy. You just say, hey, I'm always going 50 kilometers per hour or whatever it is. But when your speed's always changing, like in this graph here, how in the world would you ever express your speed for this? Well, that's when you just do what's called an average speed. You take your total distance that you're going and you divide it by your total time. So the average speed describes speed of motion when the speed is changing. So when you're not always going that constant speed. And so it's like I said, just take that total distance, divide it by the total time, and that gives you your average speed. And I've given you an example down here just to kind of show you what I'm talking about. So they're saying, well, let's say you're going to go that 5 kilometers that that bicycle was going in that last graph. And let's say it took them a half hour to go, that 5 kilometers. So that's the same equivalent as 0.25 hours in a decimal number. So you would just do the math, plug it into that same equation that we just learned. So 5 divided by 0.25, that's 20 kilometers per hour. So you were going about 20 kilometers per hour the entire trip, give or take. Obviously, you were not going 20 kilometers per hour the entire trip. That just doesn't make sense, but it's good enough for what it's for. Now, we have this thing called instantaneous speed. Instantaneous speed is the speed at any given point in time. So this is what you see when you look down at your speedometer. So like you're in a car and you look down and you say, whoa, I'm going, 90 miles per hour. I'm going way too fast. Okay, that's what a speedometer shows. That's the speed at that given point in time. So if you're speeding up, you're slowing down, your speedometer is showing you that. So if you're speeding up or slowing down, your instantaneous speed is going to change. If you're at a constant speed, your instantaneous speed is not going to change. So, like for example, I like to use the idea of you're in a car, you press down the gas pedal, what's going to happen? You look down, the speedometer is going to go up. You hit the brake, what's going to happen? The speedometer is going to go down. Okay, so those are your instantaneous speeds. Okay, you're in a car, you have this nice thing called cruise control that sets the speedometer, so always at whatever. Maybe on the interstate you're going to set it for perfect 70 so that, the cops don't pick you up. Okay, So that means that your instantaneous speed's not going to change. It's always going to be 70 miles per hour no matter what. That's the idea. Okay, in physics class, in general, we like to graph motion. And in fact, I saw some of this on the Algebra ECA last year, so you may want to, some of those Algebra 1 students, you might want to perk up a little bit and make sure that you are able to graph motion. The idea is to make distance time graphs. A distance time graph is exactly what it's called. It means putting distance and time on a graph. You must understand, first of all, that the time is always plotted on the horizontal axis, or what we call the x-axis. So hopefully everybody knows that the x-axis is down here. And the distance is always plotted on the vertical axis, which we call the y-axis. Some things about distance time graphs that you need to understand. First of all, straight lines mean that the objects are not moving. That the object is moving at a constant speed. And the other thing that you need to understand is that on a distance time graph is that the speed is the slope. That's just a few things that we're going to talk about right now about speed. We'll do some fun labs and other things that hopefully will get you so that you will feel a little bit more comfortable with the equation and with the idea of speed.